Hi, so I'm Kelly, and I work in the Cognitive Neurophysiology Lab under Dr. Martinez. And I collaborated with Nathan to create this presentation as sort of a pragmatic guide for the application of normal statistic tests. So let's start with the basics. Every continuous random variable has a probability density function associated with it. This allows you to calculate the probability of a given outcome. Let's see, how does this work? Okay. Of particular interest is the p-value, which is the probability of obtaining a certain function if you assume the null hypothesis. So the rationale is that the probability of obtaining a certain value is quite small, say 5 or 1%. Then you can reject the null hypothesis with 99 or 95% confidence. In other words, the p-value, if the p-value is less than the significance level alpha, you can reject the null hypothesis correctly. So here's your p-value. And the significance level is determined by the confidence interval, which determines the level of uncertainty in your population parameter and is dependent in part on population size. So let's get into normal distributions. The normal distribution is a continuous probability distribution, which is defined according to the Gaussian function. The shape of the normal distribution can be completely described by two parameters, the mean and the variance. And the canonical example is the standard normal distribution, which has a mean of 0 and a variance of 1, a deviation of 1. So it's important to ascertain whether your data is normally distributed, as the hypothesis tests you might use later on are predicated on this assumption. So among these tests are Skewness and Kurtosis, Shapiro-Wilk test, the Kolmogorov-Smirnov test, and the QQ plot. Kurtosis is a measure of the shape and of the probability distribution of the function, specifically the peakedness and the tail heaviness. A high kurtosis indicates a sharper peak and thicker tails, as you can see here. For normally distributed data, this test should yield a value that's close to 3, or if you use the excess kurtosis, it'll be close to 0. And another measure of shape is skewness, which measures the symmetry of the normal distribution, of the probability distribution. If the value deviates from 0, it's probably not normally distributed. So the MATLAB code for this is the Ski-Kurt test, which combines the statistics of kurtosis and skewness and gives a p-value that compares the skewness and kurtosis to the sample to the standard normal distribution. And you can find this function on the file exchange in MATLAB. So one of the tests of goodness of fit is the Shapiro-Wilk. And this tests the hypothesis that a sample with an unknown mean and variance is not significantly different than a normal distribution. And you can use the MATLAB code SW-test, also found in the MATLAB file exchange. The function returns a p-value and a decision based on the comparison between the p-value and a predefined significance level. But the decision, I mean, you can just look at the p-value and see if it's lower than your significance level. So here are some example distributions and the respective Shapiro-Wilk p-values. So you can see sort of a noisy one, a bimodal one, and one that looks quite normal. And as you can see, the p-value is significantly different, or is lower than the significance level of 0.05 for these first two, and then is not significantly different in this one. Another way to assess normality is to create QQ plots, which give a graphical representation of the normality, but no significance value. This is annoying me. Okay. So in order to construct a QQ plot, you divide the data into Q equal sized subsets called quantiles. and sort ascending according to the highest value within that quantile. And then you plot the quantiles of your sample data against those for the standard normal. And a 1-to-1 ratio would denote the distribution as normal, which is shown by these red dotted lines. And as you can see, the QQ plot gives a pretty good estimation of which ones are actually normal. So there are some limitations to these tests, well, to the Shapiro-Wilk test. Namely, the size of the sample must be between 3 and 5,000. Therefore, it's a good idea to also look at QQ plots to confirm your results. And it's important to remember the caveat that these tests are much more sensitive to departures from normality when the sample sizes are large than when they're small. So here you can see the effect of increasing sample size. And you can see that the Shapiro-Wilk test is quite sensitive to these higher sample sizes. Obviously, these are normally distributed if you look at the QQ plots, but at these high sample sizes of 100,000, you actually get an SW value that is significantly different. So another goodness of fit test is the Kolmogorov-Smirnov, which compares the cumulative distribution function of the standard normal and the sample. So the cumulative distribution function is just the integral under the PDF from -infinity to a given x. And the KS test looks at the maximum distance between the two CDFs and translates this into a p-value. In MATLAB, you can use the function KS test. So as to the relative advantages of each test, the Shapiro-Wilk test has the greater statistical power compared to the Kolmogorov-Smirnov test, but the KS test can be used to compare any two distributions of any shape, so it's much more versatile. So there are several commonly used tests that detect a difference in the group means, including the t-test, the z-test, and ANOVA, and there are several variations on ANOVA. So any function that tests the null hypothesis is called a test statistic. For example, a t-test yields a test statistic called t, which is useful in evaluating whether two sample means are significantly different. If one sample changes over time when it's subjected to an experimental condition, or if a single sample mean is different than a known mean, such as the population mean. The student's t-test was developed by William Gossett, who was an employee at Guinness Brewery, who wanted to analyze the chemical properties of the raw ingredients used in the brewing process, but had to account for small sample sizes. The story is Gossett published a paper on the t-distribution under the pseudonym student to protect the company secrets and quality control. So you can thank beer for the t-test. So the outcome of the t-test can be evaluated in terms of p-value. It's useful to use a two-tailed t-test if you expect a more extreme outcome for the alternative hypothesis compared to the null hypothesis, but maybe you don't know whether it's going to be too high or too low. You would use a one-tailed t-test if you expect the condition has an enhancing or a suppressing effect. So this test is usually utilized if previous knowledge of the experimental conditions leads you to believe it will change in one direction or the other. And as you can see, for two-tailed t-test, keep in mind both tails contribute to the p-value, whereas in one tail, it's just the one tail that contributes. So when is it appropriate to use a t-test versus a z-test? Let's look at t-test first. For our purposes, we'll focus on t-tests that assume the distribution of the sample mean follows a standard normal distribution for the null hypothesis. So it should be noted that there's a difference between the population mean and the sample mean. So the sample mean is obtained by sampling a random variable n times and taking the means of each of these samples. The t-test assumes that the data is sampled independently and that the variance is the same for both samples. Also, t-tests are best for small sample sizes, such as n less than 30. For the z-test, it assumes pretty much, it has basically the same functions or assumptions as the t-test. However, if it assumes normal distribution only for small sample sizes, but assumes no distribution for larger ones. And it can be used for small or large sample sizes. So there's limitations to both of these tests. The sample size should be as similar as possible, but there's some leeway. And a null result does not necessarily mean that the samples are the same, simply that the test fails to detect the difference. As a non-parametric alternative to these tests, you can use the Wilcoxon rank sum test. And you might ask, why would you use a t-test if you can use the Wilcoxon rank sum test for any distribution, regardless of its shape? And that would be because if you do know the distribution to be normal, the parametric tests, such as t-test, actually have greater power than the non-parametric tests. So an ANOVA is a generalization of the t-test that can compare the means of 3 or more groups. The ANOVA tests the null hypothesis that all of the groups being compared originate from the same population. Similar to the t-test, it assumes normal populations, independent samples, and homogeneity of the variance. Within the realm of ANOVA, the f-test tests the hypothesis that the means are the same. The f-test statistic is a test on variance homogeneity, which is the idea that the variance is the same between all groups being tested, and examines the ratio of the variance between treatment and the variance within treatment. So it's a way of determining whether the means are different by examining the variances. So clearly these two distributions have different means. In MATLAB, you can use the ANOVA1 function, which gives the F statistic. A higher ratio would mean that the variance between the groups is greater than those within the groups, and thus the sample means are probably different. So there's a few common variations on ANOVA, and these can be used to fit your experimental designs. The two-way ANOVA examines 2 independent variables, which we'll call factors. For example, if we examine the effect of gender and race on wage, we can consider the effect of each factor alone and the combined effect, which is called the interaction term. In MATLAB, the function ANOVA2 returns 3 p-values, 2 of them testing the null hypotheses that the samples from factor A or from factor B are from the same population, and then 1 testing the null hypothesis that the factors do not have any interaction. Another commonly used ANOVA is repeated measures ANOVA. And this one is applicable if you are using the same set of data, but taking multiple measures on it, such as in longitudinal studies. For example, if you're looking at the health of some patient population measured at baseline, and then again after the therapeutic intervention. So for the repeated measures in MATLAB, you can use the function ANOVA-RM, also found on File Exchange. And the output is a p-value, which can be used to assess if there's a significant difference between the groups. So of course there's some limitations to ANOVAs. One limitation is that it works poorly in unbalanced experiments in which the sample sizes are not very similar or not very equal. If the assumption of normality is not applicable, you can always use these non-parametric tests, the Kruskal-Wallis test or the Friedman test. So this presentation sought to give you practical tips on the usage of normal distribution tests, tests for normality, and the hypothesis testing. Hopefully you've gained a better understanding of the advantages and limitations of each of these tests. Any questions? Yes.
So I had a question. I know that usually, like maybe this is just that I'm lazy, but I don't normally test for normality. But I use a t-test, and usually I find whenever I do that, whatever distribution I have is not normal. I guess because the sample size is so big. You know, say you have like 100,000 spikes or something like that.
Mm-hmm.
Do you know, or maybe somebody else a way around that? Like, do you just take some subset of the sample, so you have a small sample size, and test on that, or are there tests for normality that are okay with?
You'd probably just use the Q plot as a starting point and also assess the kurtosis and skewness, which don't seem to be so sensitive to sample size, and sort of get a heuristic as to whether it's probably normal or not. Anybody? Anybody else? Yeah.
The ANOVA repeated measure ANOVA.
Mm-hmm.
What's the difference between doing ANOVA, the same repeated measure, so you have the same patient,
Mm-hmm.
and you have before treatment, after treatment. So what's the difference between doing the repeated measure or using ANOVA?
Oh, just doing it twice.
Yeah.
I just think that the repeated measures ANOVA actually has more power than simply doing it multiple times.
Is there is it unbiased? Do you think that there's a bias that comes from using ANOVA multiple times if it's not?
I'm not sure about that.